All right. Hi, guys. It's good to be back here in the studio of Sofia Tech Park. Welcome to the show. This is Ratio Online. And most of you haven't seen us for a while, and there is a good reason for that. We were extremely happy to actually restart our live events recently, so we've been doing quite a lot of these days. But now we decided to make a compromise, so to say, and we're back in the studio because we have a very special guest today. We don't get people from NASA very often, so I'm looking forward for this talk, and I'm sure that there are many geeks right now watching us that will be extremely interested by the topic that we will be covering today with our guest. Now, what is this topic all about? Now, little that you know, right now there is an international fleet of spacecraft that is roaming the solar system, and it's accumulating like huge amounts of data. Now, accumulating data is one thing, but making sense of it and making it useful is a whole different thing. So there is a special project for that, and I'm gonna articulate. I'm gonna try to articulate it well. It's the NASA Solar System Trek project. Now, the idea of the project is to make access to this data like way too easier. So you enter a browser-based interactive visualization of the data. There are like analysis portals. And you can do quite a lot of different things there if you are just interested in it, or you are a proper scientist who wants to use this tool for his scientific purposes. But you can do different things. I mean, you can explore Mercury's surface. You could look at Apollo 11's surface, like landing side. Plenty of very interesting stuff that today we will show you how you can do. Today we'll be speaking with Brian Day. Now this is a mouthful again. Brian is a deputy staff scientist at NASA's Solar System Exploration Research Virtual Institute, and he will tell us, more about NASA's most exciting and forthcoming missions into the outer space, and he will talk about the Solar System Trek portals, and he will share some insights of like its most exciting and useful applications. Brian, can you hear me, sir?
Yes, I can. Thank you,
Welcome.
Petko.
Welcome to the show. How are you feeling?
Very well, thank you. Very well. Thank you for having me.
Sure, it's really a pleasure and a privilege. As I said in the introduction, we don't get NASA people very often. We work closely with the European Space Agency, with which I see and I hope you're collaborating well. But NASA being a little bit further away from us is a really special thing. So we're really delighted to have you here today. And as I said, there are plenty of geeks right now watching who are looking forward for your talk. So you have quite a big responsibility here, right?
Good.
Good. Okay.
Good.
So I'm going to give you the stage right now, Brian. You guys listen carefully to what Brian has to show us and say. And in the meantime, think of any questions that might come up. And you can submit it on sli.do or Slido, as we said, with the hashtag Trek. And I'm going to make sure that during the discussion panel with Brian, I will pass your questions to him. So, Brian, without further ado, you have the floor, sir.
Very good. So I will share my screen here if I can. And so again, as Petko said, I'd like to introduce you to NASA's Solar System Treks portals. And the Solar System Treks is a collection of web-based portals that allow you to access data from many different instruments aboard many different spacecraft across the solar system. You don't need to buy anything, you don't install anything, you just point your browser to trek.nasa.gov and start exploring. We have portals for a growing number of worlds where we have sent spacecraft. This is international missions from everywhere, and we are looking at a variety of planets, moons, and asteroids across the solar system, and we've continued to grow this list. I'm going to start out by focusing on the moon, because that's where we started out. This was our first portal. And the moon right now is of course, great interest because we have the Artemis program that is about to send a series of robotic missions and also human missions to the surface of the moon. And one of our target areas of interest, of course, is the South Pole. So here we are using high resolution, narrow angle camera imagery from the Lunar Reconnaissance Orbiter, looking straight down at the South Pole of the moon. You see the crater Shackleton in the center here, and the South Pole is just on the edge of Shackleton. And as we look at the South Pole, we see that much of it is obscured by shadow. That's because the sunlight is coming in essentially horizontally. And therefore, many of the craters near the South Pole of the moon have their floors in permanent shadow. Some of these craters' floors have not seen sunlight in well over 1 billion years. And because they are so dark, they are very, very cold. This shadow can make it difficult to actually plan exploration. But if we change our view to a different instrument, in this case, the laser altimeter aboard the Lunar Reconnaissance Orbiter, we can pierce those shadows and we can see the detail down inside those shadowed craters. This helps us make planning a lot easier. We can also look at a slope map, and we can color code slopes so that blue is relatively flat, orange here is probably too steep to be driving a rover down. So again, this helps us plan our traverses. We can overlay those areas of permanent shadow. And these areas are really very interesting to us because they are so cold that these are areas where water ice can potentially accumulate. And that, of course, can be a very valuable resource for us if we're planning to live and work on the moon. As we search for water, another way of viewing this same area might be looking at temperature. So here we're using the Diviner instrument in orbit around the moon to look at the average temperature or maximum temperatures. So again, this can help us figure out those locations where we might want to go for the precious resource of water ice. Using the LAMP instrument aboard the Lunar Reconnaissance Orbiter, we can even image what appear to be deposits of surface frost. We can use neutron spectrometry to sniff out deposits of hydrogen. And that hydrogen is, at least in much of the cases, bound as part of water molecules. So again, this can help us search out the deposits of water ice. And here, using thermal modeling, we can look at a map of ice stability at depth. How far would you have to dig down to get to a temperature where ice would remain stable? And in some of those permanently shadowed areas, you don't have to dig at all. Ice would be stable right at the surface. So also, we can zoom down and take advantage of the resolution, the extreme resolution of the narrow angle camera aboard the Lunar Reconnaissance Orbiter and get to details that are even less than 1 meter across. This is a very exciting way to explore the surface. Now I want to show you another view, another way of how these different layers can work together. We are looking at the Marius Hills, one of the most spectacular concentrations of volcanoes on the surface of the moon. But if you look at this photographic view, this is through the wide angle camera on Lunar Reconnaissance Orbiter, I admit this does not look too spectacular. But if we change our view to that seeing by the laser altimeter, where we can precisely measure all those ups and downs, now you can see how those volcanoes really pop into view. Now let's look at this same area in a completely different instrument. This is a gravity map from Japan's Kaguya spacecraft. In this case, low is blue gravity, red is high amounts of gravity. And you can see we're looking at the same area, but with a completely different view. But as you add these different views, you can do amazing things with these different views. You can put them into layers and you can reorder them. You can toggle visibility, but most importantly, I think, is you can adjust transparency. This allows you to blend different layers. So here we have blended the laser altimetry view and the gravity view. And so this allows us to actually see the surface details of that volcanic field. And at the same time, through the colors there, visualize the now solidified plug of magma beneath the volcanic complex. So there are many other ways we can look at the moon, again, through these different views provided by different instruments. So our general wide angle camera view, this is how the moon would look if you were looking out the window of a spacecraft. The albedo view takes away the shadows and just shows us the difference in shading between different rocks. We can look at how the rock has weathered in the radiation environment of space. We can look at the density, how densely packed the soil is, or how rocky the soil is. We can look at different mineral abundances, iron oxide, olivine, orthopyroxene, so we can study the mineralogy. We have different ways of viewing these maps, different projections. You have a flat, equirectangular projection, or you have polar projections. But one of my favorites is to jump into 3D mode, and then you can interactively, using your keyboard game controls and mouse, fly across the surface, fly down into craters, and rove across the surface. This is really exciting. Now, we have a variety of tools that are available to help you analyze the features that you're seeing. The first set of tools is available to anyone, any member of our user base. And our user base consists of mission planners, it consists of planetary scientists, but it also consists of members of the general public who are just interested, and students and teachers, students of all ages from kindergarten through university. But this general set of tools is available to anybody in that user base. And one of the things we can do is you select a point on the surface of the moon and you can plot the position of the sun over time, both its altitude and azimuth. You can draw a path across the surface of the moon and measure the changes in elevation. So create an elevation plot. This allows you to measure the heights of mountains, the depths of craters and valleys. It's a great tool for exploring. You can also draw a bounding box around any feature you like, and the portal will return to you either an STL or OBJ file that you can send to your 3D printer. So you can make 3D prints of any terrain that you like. Another really fun feature is you can draw a path anywhere across the surface and have Moontrek return to you a QR code. Scan that QR code into your smartphone and then put your smartphone in a pair of cheap Google Cardboard compatible goggles, you know, $5, $10 goggles. And whatever path you drew, you will now be able to fly in virtual reality. We also have a series of advanced tools available for people who are doing real research or mission planning. And these are available for people who get account level access. And you can request account level access if you're doing true academic or mission research. And let's take a quick look at these advanced tools. Some of the data products we have are really huge. They cover the entire globe of the moon. And you might want to download just a small portion of that or work with just a small portion of that. So subsetting allows you to divide up these really, really big data products. A very exciting tool we have is artificial intelligence, machine learning based crater detection. If you are going to plan a landing site or a rover traverse across the surface of the moon, you might want to avoid very heavily cratered areas. And so we have tools that will actually count and map the distribution of impact craters. And similarly, boulders can be hazards for you too. So again, we have a tool that uses artificial intelligence and machine learning to identify the frequency of boulders across the landscape. You can also create high-resolution slope maps to again help you plan landing sites or plan traverses across the lunar terrain. Lighting analysis can be very important, especially if you're planning to send rovers or equipment that is going to be solar powered. You need to be able to understand the lighting over time. And so you can draw a bounding box, specify a beginning date and time, an ending date and time, and you can see how the lighting will change over your specified area over time. And you can even generate maps of watts per square meter of energy coming in case you are planning the energy budget of your solar-powered rover. The surface electrostatic potential tool is very similar to lighting, but it deals with the plasma environment of the moon. The moon doesn't have a thick atmosphere like the Earth. It doesn't have a global magnetic field like the Earth. And so it is exposed to the heavily charged plasma atmosphere coming from our sun, this very dynamic charged environment. And that can pose hazards to equipment and resources that you put on the moon. And so being able to understand the electric charging potentials of different areas on the moon is important. We also have a tool for understanding and planning laser retroreflector studies. Back in Apollo, we put fancy mirrors on the surface of the moon that we could bounce lasers off of from here on Earth to measure very precisely the distance to the moon, to start setting up navigation grids, to studying actually the interior of the moon through these precise reflections. And we're going to be adding more reflectors. And we're working with friends across the world generating new retroreflectors and sending them to the moon. Rock falls. If you look across the moon, in many areas, you will see boulder tracks where boulders have rolled down slopes. And that can actually be very valuable because those tracks that the boulders leave in the ground can give us clues about the mechanical structure of that ground, how compacted it is, what its properties are. And so again, we have a machine learning, artificial intelligence based tool to go and look for these boulder tracks across the surface of the moon. Underlying all of these tools, we have a pipeline that allows us to put together mosaics of these high resolution images and look at places where those images, different images can overlap to give us 3D perspectives so that we can generate elevation models. So we have this automated pipeline to enable us to do this. In the works, we have a line of sight tool for communications planning. This allows you to plan communications between any two locations on the surface of the moon, between a spot on the surface of the moon and a ground station here on Earth, or some location on the moon and some resource in orbit around the moon, a relay satellite. We're also taking advantage of our machine learning and artificial intelligence capabilities to put together a general purpose feature detector. Show it some kind of feature you might be interested in, a lunar pit, a low-bait fault scarp, or something like that. Give it a bunch of examples, and then it will learn from that and start going out and searching the surface of the moon for more examples. I showed you how we have an elevation profile tool, but we have all kinds of different data like mineralogy and temperature. And what we want to be able to do is draw a path across a temperature map or a gravity map or a mineralogy map and see profiles of how that data changes by location. And we also are implementing a search tool that allows you to find the very high resolution data that's available for any particular area of interest that you might have. And so this allows us to then put together the mosaics and the elevation models that'll give us fine detail about future sites of exploration. So as I mentioned, we're starting out with the moon, but we have many, many other portals taking us to other locations throughout the solar system. And so now I'd like to take a look at some of those. We have a Mars Trek portal. And again, this gathers data from many different instruments aboard a fleet of many different spacecraft that have gone to and are still in orbit around Mars. And this is a view of Mars as it would look if you were looking out the window of an orbiting spacecraft. Today, Mars is a complete and total desert. But if we change our view again to a laser altimetry view and we color code that laser altimetry, so blue is low and red is high, we can start seeing some amazing details. We can actually see ancient dry riverbeds where water once flowed across the surface and entered into a large bay that then opened up into a great northern ocean on Mars. Mars was a wet place billions of years ago. Speaking of wet locations on Mars, or previously wet locations, right now, of course, we have the Perseverance rover exploring Jezero Crater. And so what we'll do now is we'll use Mars Trek to zoom down to Jezero Crater. We can see coming in from the west an inflow channel and another inflow channel coming in from the north that filled Jezero into a large crater lake, and then water flowed out from here in the northeast. Zooming in closer, we can see a delta deposit where material was dumped onto the floor of the lake bed. And here we're marking the landing site of the Perseverance rover. We'll zoom in closer. Now we're seeing individual sand dunes. Dropping down closer, we can see how the spacecraft was smart enough not to land in the sand dunes, but on a nice smooth area. And now we can look across from the landing site, looking out, seeing that delta deposit that the rover is going to go explore. And in the far background, the mountains we see here are the actual rim of Jezero Crater. We can fly forward and take a look at the sedimentary deposits of the delta deposit in Jezero. This is where our rover will be going to explore. We can look at the breach in the crater wall where the inflow channel flowed into the lake at Jezero. And we can look at details of that inflow channel before it reached Jezero Crater. And perhaps our rover will make it out to this location. There are many other areas of interest, of course, across the surface of Mars. Mars's great Grand Canyon, Valles Marineris, is marked by titanic landslides. And it is actually a complex of actually multiple canyons coming together. Here we're using the 3D feature to go flying across the surface of Valles Marineris, the sedimentary deposits on the floor left by ancient lakes, and then up the 8,000 meter wall of the edge, the northern rim of the valley. An area of particular interest are the Cerberus fossae. These are great fractures in the surface of Mars, and our InSight mission, the Mars InSight lander, has a seismometer aboard, and it has been detecting Mars quakes coming from this area. This is an area of active seismic activity on Mars. And you can fly down and you can see how the surface of Mars is cracked open here in a very spectacular way. And it is in this area The Cerberus fossae mantling unit is this kind of dark deposit around that one crack that you see next to Zunil crater. And this is apparently the most recent volcanic activity we have yet seen on Mars. This is measured not in billions of years of age or even millions. This may be tens of thousands of years in age. It's hard to tell for sure, but what we do know is this is recent, geologically recent volcanic activity on Mars. We can also look and see skylights or pits. And these are areas where you have lava tubes, great caverns where lava once flowed under the surface, and you have localized collapses of the roofs, providing skylights into those subterranean caverns. These areas are of interest to us because while there's no water on the surface of Mars, there may still be water flowing beneath the surface. So these skylights into lava tubes could be wonderful access places for us to perhaps have areas where we could live on Mars, protected from extremes in temperature and radiation and meteoroid bombardment. But also it could be an excellent place to look for any life that might still be resident on Mars. These are fascinating structures. Now, as we plan to send humans to Mars, the poles of Mars, of course, have an abundance of water ice, but the environment there is too extreme. We don't want to subject our astronauts to going to the extreme temperatures of the poles. But fortunately, it turns out that there are two bands of mid-latitude glaciers, about 40 degrees north and 40 degrees south. And these could provide very, very accessible resources for us. And looking down, we can see examples of valley glaciers. Here's another, if you've been to the glaciers of Switzerland, this to me looks very much like looking out at the Aletsch Glacier from the Jungfrau. This is a really remarkable view. And we see things that here on Earth we would call Piedmont glaciers. See this big toe of glaciers sticking out, flowing out from between these mountains. And we can zoom in closer for a closer look at that big toe of ice coming out. Very fascinating. We also have what we call lobate debris apron glaciers that form these kind of lens-shaped ice deposits around mountain peaks. And if you look carefully, you can see glacial ridges and even a crevasse here, a Bergschrund crevasse, where the ice is pulled away from the mountain face. We have concentric fill glaciers within craters. And a wonderful story here is told by this type of crater here that we call a Rampart Crater. We call it a Rampart Crater because of the thick, pasty debris flow around it. Normally, when an impact crater happens on the moon or many places on Mars, you get dry sprays of pulverized rock. But in some areas, you get this thick sploosh of material like you threw a rock into a mud puddle. And that's pretty much what happened here. This impact that formed this crater actually ended up hitting in an area that was rich in ice. And so you had this thick, pasty, muddy flow of debris coming out. And if you look carefully, you can even see fluvial deposits where water had flowed across the surface. And then the story gets even more interesting because coming in, advancing here from the bottom, we have a lobate debris apron glacier advancing out, and we can tell the glacier is younger than the impact because the glacier is overlying the ejecta deposit from the crater. So you can see these wonderful stories that get told to you as you wander across the surface of Mars. Other stories include looking at the edge of that giant northern ocean. And we can see 3.5 billion years ago when that ocean was present. And there were asteroids slamming down, crashing into that ocean, causing gigantic tsunamis that could race hundreds of miles inland. And today we still see the scars left by their turbulent flow across the inland landscape. And we can see the gullies left by water receding, flowing back from the tidal wave back in toward the ocean. As Petko mentioned, we have a Mercury Trek portal. You can explore the planet Mercury. We have a spacecraft on the way there right now, the European Space Agency and our partners, the JAXA, the Japanese Space Agency. And we created this portal using existing data to help them with their upcoming mission. Here we see the giant Caloris Basin, an impact basin, 1,500 kilometers across. And on the exact opposite side of Mercury, we see this very chaotic terrain where the shock wave from the formation of Caloris circled around Mercury and converged again on the opposite side, completely disrupting the terrain here. As we look across Mercury, we see many impact craters, but then we also see irregular craters surrounded by light-colored ash deposits. These are volcanic pit craters where active eruptions have occurred on Mercury. Looking in many of the impact craters, we see these bright crater floor deposits, also called hollows. And this is areas where in the extreme temperature of Mercury, some of the more volatile minerals will actually boil off into space. Our Ceres Trek portal takes us to the nearest example of a dwarf planet. And here we're looking at Ahuna Mons, a giant ice volcano on Ceres. It stands about 4 kilometers tall. On Ceres, the role of magma is played by ice, water ice, slushy, salty water ice in the mantle of Ceres. We can see ancient relic cryovolcanoes. So when we looked at Ahuna Mons, we see this big, tall mountain. But that's the only one of those that we see. And we were wondering, why would we only see one? Well, it turns out in the gravity and temperature environment of Ceres, over time, a tall volcano will slowly slump down and flatten. It will flow plastically. And so you can find examples of these ancient flattened volcanoes, and you can study their topography with our elevation profile tool. Here's another example near the North Pole of Ceres. And we can see areas on the surface of Ceres where the crust is being pried apart by upwelling material within the mantle of Ceres. We can also see these great salt deposits where cryo-ice volcanism happened in the past, and the ice volatilized into space, leaving behind the salt that was in that water of the eruption. Our Vesta Trek portal takes us to one of the largest asteroids. And Vesta, when it first formed, probably formed a nice, beautiful sphere. But as you look at Vesta today, it certainly does not look like a sphere. Now, the top of it looks pretty round, but as you look toward the bottom, it looks like some of it is missing. And that's exactly the case. Because if we take a polar view of Vesta, we see this giant impact basin, Rheas Silvia, that almost destroyed the world of Vesta when this occurred about 1 billion years ago. And you can see that it also overlies an older, similarly sized impact basin called Venenia, about 2 billion years ago, about 2 billion years old. And so 2 nearly fatal impacts nearly destroyed Vesta, sending debris out across the solar system. And as a result, Vesta has that strange shape today. The central peak of the Rheas Silvia crater is actually one of the tallest mountains in our solar system. It stands over 20 kilometers tall. And that's a huge mountain for such a tiny world. We see fractures in the circumference of Vesta, where those giant impacts almost broke the entire world apart. And we see near areas of impact craters, we see this strange pitted terrain, clusters of rimless pits that show where there were deposits of ice beneath the surface. And when the heat was generated by a nearby meteoroid impact, that heat flashed the ice into steam, which expanded and erupted and formed these patterns of pits. So last year, we had a very exciting adventure with the OSIRIS-REx mission visiting the asteroid Bennu. And with our Bennu Trek portal, you can explore the data that was returned from the OSIRIS-REx mission. You can fly down to Nightingale Crater, where OSIRIS-REx gathered its samples that it is now bringing back to Earth right now as we speak. And you can also explore the surface, and we see here amongst the dark boulders of Bennu, we see a few light boulders that stand out and look very different. And they are. And in fact, examining these in detail, we see that these are likely not boulders native to Bennu at all, but these are fragments of Vesta that had been blasted off that surface and have now landed on the asteroid Bennu. Our Ryugu Trek portal gives us views of another near-Earth asteroid, the asteroid Ryugu, that was recently visited by the Hayabusa 2 mission from Japan. And the Hayabusa 2 mission successfully returned samples from Ryugu. And you can use the Ryugu Trek platform to examine in detail data sent back by the Hayabusa 2 mission. Our Cassini mission went to the planet Saturn, and it also did flybys of many of Saturn's moons. And of course, we partnered with the European Space Agency, who gave us the Huygens lander that descended down to the surface of Titan. And Titan, of course, is an amazing world. It is the only moon in our solar system that has a thicker, denser atmosphere than the Earth does. And beneath that cloudy atmosphere, we find lakes and rivers and even seas of liquid ethane and methane. Very, very frigid, very cold. But at that temperature, something that is normally a gas here on Earth turns into a liquid. And some scientists have imagined that perhaps there could be, just as there's water-based forms of life here, there could be hydrocarbon-based forms of life in these seas and rivers on Titan. But that crust of Titan, that icy crust of Titan, overlies what is apparently an ocean of liquid water. So Titan could be a very unique case of where you could have two very different types of life, perhaps. Perhaps a hydrocarbon life living in the frigid seas and waterways of the surface, and then water-based life living beneath the crust in that ocean of liquid water. Cassini visited a number of other moons in the Saturn system, and our icy moon treks provide you with ways of exploring 7 of those moons: Dione, Enceladus, Iapetus, Mimas, Phoebe, Tethys, and Rhea. And let's see here. One of our newest portals is the new Venus Trek portal. And this was exciting to announce because we just had an announcement of new missions in planning that are going to go to Venus and study this incredible world that in some ways is so like the Earth in terms of size, in terms of location, but is so different in terms of its environment. Here we see an example of a strange giant volcanic feature called a corona. And this is actually Artemis corona, a huge volcanic feature on Venus. Another new portal that we have just introduced is our Europa Trek portal. And again, this is of great interest to us because we have the European Space Agency planning the JUICE mission to study Jupiter's icy moons. And we have NASA planning a mission, the Europa Clipper mission, to study Europa. We now have good evidence from past missions, including Galileo, that the icy crust of Europa covers an ocean of liquid water, about 2.5 times the volume of all of Earth's oceans combined. This is important because here on Earth, wherever we find liquid water, we find life. Even if it's in the boiling geothermal pools, even if it's beneath the frozen ice cap of Antarctica, even if it's in the cooling system of a nuclear reactor, wherever we find liquid water, we find life. And so as we look across the solar system and find places with evidence of liquid water, this really excites us. So I invite you to join us in exploring the solar system with NASA's Solar System Treks at trek.nasa.gov. Thank you very much.
All right. Brian, that looks amazing. I mean, to be honest, I didn't expect it to be, such a visual feast. That when I look at things like that, it really feels like we are finally living in the future. That's amazing work that you guys have done there.
It really is amazing, Petko. I have to admit that even though I spend most of my days working with data like this, at the end of the workday, oftentimes I'll pull up my computer and I'll just go flying across a planetary surface. Yeah. And I'll see something I've never seen before. I'll just think, what in the world is that? What is going on here? And you stop and you look and you use some of our tools and you try and figure out the story that the planet is trying to tell you the amazing processes that go on these worlds around us. It's really a lot of fun.
Yeah. I mean, it's more fun than most of the video games that are out there, And at the same time, it can be educational. It obviously is always inspiring. It's really impressive work. And actually, the first question that popped in my mind was about its usage right now. Now, we did mention in the beginning that this is currently being used mostly, by scientists, of course, by the open public as well. But going back to my school years, I can only hope that I will get, a glimpse of the solar system, even remotely close to what you just showed us. So I guess the question is, are there any plans for this to be used as an educational tool with in schools, which are the most important, people that we must address right now?
Absolutely. And so it is being used in schools right now. And teachers are learning to use this for some really wonderful applications. And one example is, a number of years back, there was a meeting in Houston here in the United States where people from around the world got together to try and figure out the best landing sites for humans on Mars. And we got together for several days, and there were various people presenting different locations, and there was a great deal of debate and argument and rending of garments and gnashing of teeth. And but it was a very exciting process to try and figure out where we wanted to send humans. And that whole process was televised.
Oh.
And now I know a teacher who is doing the same thing with students of all ages.
Yeah.
And basically saying, okay, here's this tool, Moontrek. I want you to go out and you find a new place where you think humans should go. And then all the students get together and they have their own big meeting and debate. And they present their proposed landing site and why they think we should go there. And they end up voting and narrowing it down to their top choices. And then we've actually had the students come to NASA and present their findings to the management of NASA. And
Oh, wow.
so that was a really wonderful, enjoyable experience.
Wow, that really is wonderful. Now, is this like available to be used worldwide? I mean, how does that actually work? You know, if there are some teachers
Yes.
watching us right now, I mean, is there any copyright
Yes,
or something that they need to consider, or they can just go and just use it? Yeah?
Just point your browser to trek.nasa.gov and feel free to use it.
All right, that's really awesome. Now, when we speak about the broader public, do you have any specific examples that you can show on how citizen scientists are actually contributing to to the general knowledge that you are acquiring? I mean, how can we be helpful? Yeah.
That's a really good question. And so there is a group of amateur astronomers that focuses interest on the moon. And these folks are really good. I mean, you'd be amazed with amateur telescopes today and the kinds of cameras that they can put on these. And then you do computerized sharpening of images. These guys are getting images that look like they were taken from the Lunar Reconnaissance Orbiter.
Right.
This is really good, valuable data. But what we are finding is using Moontrek can be a valuable tool for them in finding targets that they want to image and interpreting the targets that they find in their telescopes. And then what we're looking to do is with the upcoming Viper mission. So Viper is going to be a robotic rover that will go to the south pole of the moon and is going to prospect for water ice. It's scheduled to launch in 2023, so coming up fairly soon.
Yeah.
And of course, as we mentioned, the lighting conditions at the South Pole are very harsh. And one of the things that we're hoping to do is have, again, this amateur astronomy community imaging the South Pole of the moon while we are there and looking at the changes in lighting conditions as seen from here on Earth. We'll also get, of course, a view from the Lunar Reconnaissance Orbiter, but we'll be able to study those dynamic lighting conditions from multiple different perspectives. And again, we'll have the assistance of the amateur astronomers, and they can help plan their campaigns using tools like Moontrek.
Yeah, and of course, and at the end of the day, the more brains are involved, the better. Yeah, and yeah,
Absolutely.
That's really awesome. Now, in terms of the objects that are being mapped and put on the portal, how soon or how much time does it take from taking the raw data from the spacecraft until it's actually uploaded on the platform? I mean, how much time does it take, this whole process?
Oh, so that's something I need to point out. We do have this brilliant team of engineers at NASA's Jet Propulsion Lab in Pasadena. And so I need to tip my hat to all of them. And they can put together a basic portal within a year's time. Now, this is something to make clear, is that as we look at these portals, these different portals, you will see different levels of detail. Right. For instance, the moon has thousands and thousands of different data layers, whereas something like Saturn's moon Enceladus is very basic in comparison. That's because Some of these objects we have been to with a great many different spacecraft, and we have spent many years orbiting around these. And so we amass a great deal of data. In the case of the moons of Saturn or Jupiter, we've never orbited any of them. We've done a series of flybys. And so we get, different views of a small piece of that world. And we'll get these different views at different times and at different distances, and we kind of patch those together. And so in some cases, some worlds like Mars and Mercury and the moon, where we've spent a lot of time in orbit, we can gather a lot more data than some of these other worlds. So a very simple portal can come together in a matter of months to a year, whereas a very complex portal is years in the making.
Yeah, that's something else. Yeah, you did mention that additional capacity or additional spacecrafts are obviously needed in order to map all these objects that we see in the solar system. So I guess that you guys are very excited, as all of us are actually, to get a fascinating, a great Christmas present with the launch of the James Webb Telescope. So is this going to be the most powerful tool in your toolbox when it comes to, studying the solar system, or is it going to be pointing a little bit more further away?
Yeah, the James Webb Telescope does have, of course, potential for doing solar system studies, just as the Hubble telescope has delivered some wonderful imagery for us of the solar system. But like Hubble, I expect to see James Webb focus a lot of its attention on much more distant subjects. Now, I'll point out that when it comes to detail, real fine detail, our best data still comes from spacecraft that we send directly to those worlds. So once we get into orbit around Mars or the moon, that's where we really get our most detailed views, is by those close-up vantages.
Right. When we speak of spacecraft like that are orbiting these space objects, I mean, one of the most impressive feats, at least from my point of view, is to actually go around an asteroid or land on a comet. And we have seen that the most recent mission that has as a goal to study these asteroids is the Lucy mission that was very recently launched. So can you tell us a little bit more about this mission and what is it about to the general audience?
So Lucy is a fascinating mission, and it's a very ambitious mission because it is going to study a very different population of asteroids than we have previously explored. We know of a population of near-Earth asteroids like Ryugu and Bennu that are close to us here on Earth, and those are good to study from a safety standpoint. Then, of course, there are the asteroids between the orbits of Mars and Jupiter in the classic asteroid belt.
Yeah.
But we also have, sharing the orbit of Jupiter, we have what we call the Trojan asteroids, in a clump kind of ahead of Jupiter and another clump behind Jupiter, orbiting in that same path that Jupiter orbits in, occupying these neat gravitational niches called Lagrangian points, where things can essentially park and move in gravitationally safe ways. And so you have this collection of asteroids sharing the orbit of Jupiter, and we have never explored any of them. But we realized that they could be a very different population than anything we've explored yet. And so Lucy is going to do something very ambitious. It's going to shoot out to one of these populations, one of these clumps of asteroids, and then it's going to circle back, and then it's going to go to the other one. So it's going to cover a huge swath of solar system, visiting a number of asteroids in these different locations. So this is a mission that's going to do a whole lot of traveling, covering a huge amount of distance, and it's going to visit a number of different worlds and give us insights into this population of asteroids that we have never visited before.
Now, why would you expect them to be much different from the other asteroids that we have explored?
We see that asteroids oftentimes form in families. And some of these families are the results of disruptions of larger parent asteroids. And these asteroids take on different types. So some are what we consider to be stony objects that are that have gone through a fair amount of geological processing,
right?
That have gone through some differentiation, that have evolved mineralogies. Others are carbonaceous in nature. These are composed of essentially the raw building material that the solar system was formed from. Relatively unprocessed stardust that is clumped together and can have even interstellar grains within it that are far older than our solar system, predate the formation of the sun. And then some of these are icy in nature and represent perhaps bodies from the outer solar system, from the Kuiper belt, that got jostled in and fell inwards. And so we see a very heterogeneous, a very different types of asteroids scattered through the solar system. And of course, Jupiter is, the great gravitational magnet within our solar system. And so it can capture things in ways that could end up being very useful to us. And so we want to go explore these collections of asteroids that have formed in these gravitational pockets within Jupiter's orbit.
It's a real treasure trove, right? I mean, speaking of objects like that, now we saw that you have like amazing visualizations of asteroids, but we didn't see any comets there. We have the Rosetta mission that accumulated quite a lot of data. Can we expect to have a closer view of any comets anytime soon?
Oh, that is a wonderful question.
Well, you're welcome.
We actually do have a prototype for the comet Churyumov-Gerasimenko that was visited by Rosetta.
Right.
So we have done some work on that, and I think you're right. We want to see, we've got planets, we've got moons, we've got asteroids. We need to have comets represented here, and so we've done some preliminary work on that. So I fully agree with you.
All right, terrific. Now, you as one of the leading figures in this project, you do know what is the pipeline. I mean, you have like an insider's knowledge of what is next to come, right? I'm not going to pick your brain if you don't want to share. But
I have some knowledge, but I will admit to you that we come up with ideas, but then we go to NASA management and we solicit their input and say, what are your priorities? Right. So, and I'll tell you right now, our highest priority at the moment is the moon. And so we are getting ready to launch a whole bunch new robotic spacecraft going to the moon, gathering a lot of more exciting, detailed data for the moon. And we very much look forward to incorporating that data into MoonTrek so it will be accessible to all of you.
Now, is this interest in the moon sort of like, is it provoked by the fact that we are also looking to the Artemis mission as like one of the big things that hopefully will come on time and everything will be fine. But it's the thing that I'm most excited about when it comes to NASA missions. So how is Artemis going at this point? Can you share something with us about this mission?
Yeah, so very exciting right now. The Artemis 1 launch vehicle, this SLS, has been fully stacked now at Cape Canaveral in Florida. And this is a really big rocket. And it is now being targeted for launch this coming February. This first launch, this first Artemis 1 launch, will be uncrewed. There will be no humans on board, but this will be a robotic test flight shooting out around the moon, and then having the Orion capsule coming back in at its very, very high speed, entering the Earth's atmosphere and being recovered. And so this will be our test flight. But beyond that, well, it's not going to be carrying any humans on board. It will be carrying a payload of many different smaller spacecraft that will be deployed. Some of them will go into orbit around the moon. Some of them are going to continue on outwards. Some of them will be studying the Earth, but there's going to be a deployment of many other spacecraft. And some of these, like I say, will be going into orbit around the moon, giving us new data that we're looking forward to integrating. So the Artemis 1 launch, very exciting, scheduled for this coming February. Boy, I'd love to go there and watch that. That is going to be a big, loud, exciting rocket.
Yeah.
But then, of course, then I mentioned the Viper rover. That's coming in 2023. But we've also got, at least we're targeting 2023. We also have a number of other exciting missions to the lunar surface that are being done in conjunction with our commercial partners. So the Commercial Lunar Payload Services Program, CLPS. And this is private companies that are providing transportation services to the moon. And we are putting together scientific payloads to go to the surface of the moon on those. But a whole bunch of other countries and private companies are putting together payloads that will go along too. And so it's going to be very fascinating to see this now upcoming explosion of just a huge number of scientific and commercial efforts on the moon. It's going to become a whole lot easier and cheaper to get something down to the surface of the moon. Yeah. So start planning your experiments now, because this kind of accessibility is happening.
Yeah, I mean, it looks like a very exciting time. I mean, it seems like there is a flight every week, a mission every week from the Chinese, from the Russians, from the European Space Agency. I mean, the space is getting a little bit crowded now. One of the topics that is of great interest to me is Venus. I mean, as you said, it's an amazingly beautiful and sort of mysterious planet, right? Especially in light of the recent news. I even remember when I heard this for the first time, when they discovered phosphine there. I genuinely there for a few seconds thought that this is it. We discovered life on Venus. So do you think that the acceleration that we are seeing right now, especially when it comes to Venus, is a result of this discovery? I mean, is there something going on around Venus that we don't know about, or?
We have been fascinated by Venus for a long time. And one of the things that I think is perhaps most interesting, I mean, the discussion about phosphine, of course, grabbed the news quite a bit. There's a lot more work that needs to be done in that area before we're sure what's going on. But one of the things that we see evidence for is that Venus's environment used to be much more like the Earth's than it is now. There's good reason to conclude that Venus perhaps not all that long ago, geologically speaking, had an ocean of liquid water. It could have been a very habitable place. But Venus, of course, has gone in a very different direction.
Yep.
And our understanding of the greenhouse effect and the hazards that that effect poses for us here on Earth, our understanding of that greenhouse effect, to a fairly significant degree, comes from our study of Venus and our understanding of Venus. Venus is the perfect laboratory to understand the greenhouse effect in its most extreme case. And so we have an opportunity here to learn some very important lessons as we study Venus and see a world that was essentially the size of the Earth, occupying just a next door location, may have once been very habitable in a way very similar to the Earth, but because of this greenhouse effect, has gone in a very dangerous, precarious direction. There are lessons there for us to learn.
Yeah, hopefully when we look at Venus, we're not looking into the future, but there are definitely some inconvenient truths that are hiding there. I think Carl Sagan was actually one of the pioneers of the study of Venus when it comes to this effect. So it's been decades now that we actually understood that. So we just need to. We just need to be more effective in affecting the public mind, when it comes to that. Well, of course, many people are now thinking of Exodus. It's like, okay, so we're doomed. So what do we do about it? So we're looking at the near solar system, and especially to some of the moons that you actually mentioned. So like the most exciting one, probably Europa. For the reasons that you already stated. Now, are there any missions being planned to visit Europa, considering what we know about it and how exciting it actually looks?
Absolutely. So, yes, the European Space Agency has its Jupiter Icy Moons, or JUICE mission planned, and NASA is planning the Europa Clipper mission. Those will be the first of what I suspect will be multiple missions going to Europa. So you're right, Europa is an irresistible target. There's still a lot that we just don't know about Europa. We've gotten tantalizing hints, largely from the Galileo mission. But one of the things we still don't know is really how thick is that crust of ice? How accessible is that ocean? Yeah, we don't know. So we see areas of ridges and rifts, and we see areas of chaos where it looks like we have rafts of ice floating perhaps on a very, very thin crust. And you have different interpretations of the data, and so, how thick crust. And you can read the data in different ways, but the basic answer is we don't really know at this point. So we need these missions to go and give us a better understanding of Europa and get a better understanding of that ice crust and the ocean that apparently lies beneath it. And these first missions will be space-based, looking down upon Europa, but eventually we will get to a surface mission. And there are all kinds of ideas being developed by researchers around the world of penetrating that icy crust and getting down into the ocean beneath. That's really where we want to do a lot of exploring. But of course, first we need to understand better the true nature of that icy crust. How thick is it? Where might our best points of access be?
Yeah. So quite a lot of work to be done before we
very much so
before we actually do that. Now, I already mentioned the proverbial Exodus. I also mentioned the James Webb Telescope. So it's more it's natural that we start looking further away, and especially this fascinating topic of exoplanets. So going back to the trek, do we expect at some point to actually be able to visualize exoplanets the similar way that we can do right now with the near objects?
Probably not in any time soon.
Yeah.
Getting that level of detail of an exoplanet is going to be very, very hard. Getting the kind of views that we have from low orbit around a planetary body is very different than what we'll get from even our biggest telescopes in space. What the biggest telescopes, something like the Webb, may be able to do, though, is analyze the atmospheres of some of these exoplanets. And what we're especially interested in is looking for possible biosignatures, signs of perhaps existent life, former life, or chemistry that would facilitate life. So we can expect some really fascinating findings to come from the James Webb Telescope when it comes to exoplanets.
Well,
and I'll just point out too, some fascinating news that we just apparently have. I just saw this morning, detected the first exoplanet in another galaxy.
Oh, wow.
M51. So the exoplanet list may be expanding beyond the limits of our galaxy. So, wow. Yeah, it's exciting times we live in, isn't it?
Yeah. Woo! All right. Now, we have a request here. Can we make a trek of all the moon landing sites that we can actually deeply explore? I mean, can we do that in the existing trek that we currently have?
So we have all of the Apollo landing sites represented, except for Apollo 17, which we will be adding soon. But we can actually, if you want me to, do we want to jump into Moontrek Live and fly down to the Apollo landing site, the Apollo 11 landing site?
Sure. Can we do that, guys? Yep. The guys are saying that they can do that. We just need a second.
So I'm going to share my screen.
All right.
And let's see.
It'll be really cool if we can see the step.
Okay, so I'm jumping into Moontrek here. Are you seeing Moontrek?
Yes.
Okay, so let me see if I can get this. So here we go. We have what we call bookmarks, and one of them is Apollo 11. So here you can read about Apollo 11, a little bit of background. We'll add the data. We'll fly to the area. And here we see a variety of markers for interesting things, but I'm going to turn the markers off for the moment. And we'll just go ahead and zoom in. And here, if you look closely, we can see the descent stage of the lunar module.
Whoa, no way.
We can see the, so lunar module descent stage, the seismometer left behind, the lunar retroreflector. Remember we talked about retroreflectors. Here's Little West Crater. But look very carefully here. Do you see some dark squiggly lines across the surface?
Yep.
Those are the actual footprints of the astronauts.
Oh my God, this is so cool.
So yeah, the answer to your question is yes, we can do that.
Wow, that's really fascinating. We can probably see the golf balls that they played with at some point.
I haven't found those yet.
Right. Now, in the coming soon section of the trek, we see Earth. What is that all about? How is that going to look like?
So we have ideas for what we want to do with Earth. And there's no point in recreating Google Earth. That already exists.
Yeah.
But what we want to do, perhaps, is something special. And so I'm giving a sneak preview here. What we're thinking of is taking a look specifically at sites here on Earth that we go to do what we call analog studies. So I know my friends at the European Space Agency do this a lot. Bernard Foying has involved with many analog studies, and I have done a number of these. We go to places here on Earth that geologically or environmentally have things in common with destinations elsewhere across the solar system.
Oh, so like
for instance,
Iceland or some
Mars,
deserts or, yeah.
Exactly.
Right.
Exactly. And so for instance, I've gone to the Atacama Desert in South America, this incredibly dry desert. And it has been arid to hyper-arid since the time of the dinosaurs. And it is, if you want to find a place that really looks like Mars, that's right up there. Same thing with the dry valleys of Antarctica. They're really incredibly harsh places you can go that are great places to figure out, how we're going to live and work in locations across the solar system, but also studying how life might adapt to very, very harsh environments like perhaps we might find on Mars. So what I am hoping to see in our Earth Trek portal is a focus on gathering the science of these analog locations across the surface of the Earth.
Very cool. All right, a question here that I'm not sure you're the right person to ask that, but I'm just gonna give it a try. Is there an economic roadmap for the business opportunities on asteroids or the moon? A plan that quantifies potential returns? I guess the question is, do we have an understanding whether it's worth it?
There are a lot of companies that are working on business models for this and are looking at potential returns on investment. A lot of that depends, quite frankly, on a better understanding of the resources that we find out there. Some things that really have attracted a lot of commercial interest are the asteroids that seem to be essentially shards of metallic cores left behind from the disruption of larger differentiated asteroids. And so if you have these very metal-rich asteroids, some people see potential, great potential economic returns from those. Of course, we haven't been to one of those yet. So that's a key, but that's coming up. We have one called the Psyche mission that is going to go to the asteroid Psyche that appears to be one of these metallic bodies. And so we'll get better insights. Now, I know the country Luxembourg has done a great deal of research into looking at the mining potential across the solar system. So work is being done on that, and it's an international thing. I guess I would recommend to your audience one great resource that you have there in Europe is the European Planetary Science Congress, EPSC. It meets every year, different locations in Europe. Of course, the last couple of years have been virtual meetings, but normally it is an in-person conference, and all variety of topics in planetary science are discussed. A few years back, there was one it happened in Riga, Latvia. It's a wonderful thing. It's a wonderful conference that I would recommend you look into.
Right. Now, probably a last question, Brian, and I'm gonna make a personal remark here. Now that we are all seeing this abundance, as I said, of like different players in space, I have sort of an ambivalent feeling about this whole thing. I kind of crave the more romantic times when NASA was the major player, or God forbid, the Soviet Union and all of that. Now it seems like the aesthetics sort of change. That now that we see space tourists, especially people that I personally dislike, waving us from space. So something is being lost there, I think. So I guess my question to you is, how do you feel about this whole thing, the commercialization, the space tourism? How do you feel about that? I don't want to put you on the spot here, by the way, because you're
No,
representing an institution.
I understand. I understand what you're saying, Petko. I am. This may shock your audience, but I am a little bit older than you are.
Yeah.
And I do remember. I can remember the first space flights.
Yeah.
And I can remember Yuri Gagarin and Alan Shepard going into space, and I have very clear memories of the first astronauts walking on the surface of the moon.
Oh my God, you're that old, Brian.
I am that old, yes. And I've had the pleasure of getting to know a number of the explorers who did walk on the surface, a number of the Apollo astronauts. Truly special people. You're absolutely right. But I am also part of what is called the Apollo generation. A generation of people that was inspired by the missions of Apollo and ended up going to school, going to university, studying math, science, and engineering, and fueling the technology boom that we now see today. And while I cannot view the space tourism in the exact same light as what I saw my personal heroes going into space, it's the view is definitely different. But at the same time, I greatly appreciate the potential that perhaps in my lifetime, I will get to go and see that incredible view.
Yeah.
I mean, William Shatner was 90 years old and he just got up there. I've got a few years to go before that. So, there is a chance, when I think of how inspired I was by these first ventures into space, and now to think that perhaps I might have the opportunity to experience that incredible view myself, damn, I'd do that in a heartbeat.
Yeah. Well, I think this is a good moment to conclude our conversation, Brian. Thank you very much for being so generous with your time and for putting the effort to show us this amazing, amazing tool. Thank you very much again for joining us, and I hope that you remain as productive, and I wish all the best to you and your colleagues at NASA, because I think you are doing something very important for all of us. So we really appreciate the work that you guys are doing there. So thank you very much, Brian.
Thank you so much. I really appreciate the opportunity.
Thank you. All right. Well, so this concludes the event today. Thank you very much for joining us, guys. I would really recommend that you try this tool. I've tried it myself, and it's absolutely fascinating, inspiring. Thank you very much for watching us. Stay tuned for our next event. Hopefully, they will be live. We're still not sure here with our colleagues, but sure enough. Stay tuned to our website, ratio.bg, and or our social platform. So just follow us and just make sure you follow our calendars to see what else we are cooking for you. Of course, we want to thank our partners from Melon. Melon is a software company, one of the very few actually in Bulgaria who have dedicated themselves to help us communicate science. So thanks very much to Melon. You can check them out on their website. They like looking for amazing talent such as yourself. And of course, thank you to all these people that you're currently seeing listed there. These are our personal contributors, our Patreons, who are helping us out in this difficult effort to communicate science here in Bulgaria. Thank you, guys. And if you do want to support us, you can go to patreon.com/RatioBG, or you can just, continue consuming any of the things that we are doing. We're doing podcasts, all kinds of like virtual and live events. So follow us on all the social platforms, and stay tuned for our next events. Thank you very much, guys, for joining us, and I wish you all the best. Bye.